Hey folks, in this video we're going to be talking about writing noble gas configurations or noble gas electron configurations. Kiss that noble gas ring. So I want you to be able to explain why a noble gas configuration is most stable and also the octet rule. And I would like you to be able to use the noble gas configuration shortcut for writing electron configurations. Yeah, I want to look at some fuzzy friends, so we're going to talk about the octet rule as a new vocab up in here. So, electron configurations for noble gases. 1s. What? Oh, right. So I have my electron configuration for helium here, and as I keep filling up shells, I get to the 1s2, the 2s2, and once I filled up my 2p's, I have neon. And then I start filling up shells again. All right, I filled these guys, and then once I get to a full 3p, I'm at argon, and I keep filling up shells. I keep filling up shells. When I'm at a full 4p, I am at krypton. And this keeps going. It's no coincidence that every noble gas is going to sit in this row, so they all have filled p subshells. And if we look at how many valence electrons each one of these guys have, they have full, for neon, the second shell, so 2 here and 2 here, so 8 valence electrons. If we look at argon, its highest energy level is the third with 2 in the s and I can't say my words. 2 electrons in the s subshell and 6 electrons in the p subshell for 8 valence electrons. If we look at krypton, the highest energy level filled here is the 4th with 2 electrons in the 4s and 6 electrons in the 4p. So each of these are going to have 8 valence electrons and completely full subshells. This is part of what makes noble gases so cool. The fact that they have all full subshells and 8 valence electrons. And so here we can see what I just summarized. The 2s and the 2p give us 8 valence electrons. The 3s and the 3p give us 8 valence electrons, as do those 4s and 4p subshells. So here we can see this again. All noble gases have full s and p subshells. And this is going to give them all 8 valence electrons, with the exception of helium, who only has 2 electrons. And so they have this full outer shell. After the p subshell, a new subshell starts getting filled. So when we fill up the p's, we are left off with our cool noble gases. Part of the result of this is when all of those shells are full, they're going to be much more stable. Full shells are happy shells and are very stable. In fact, they're most stable when they're full or empty. They're kind of stabilized by being half full, but they're happiest if they're totally full or totally empty. So this brings us to that octet rule. You may have noticed all of those noble gases had 8 valence electrons. Elements want to have 8 valence electrons. They want to be nice and stable like those noble gases. And this seeking 8 valence electrons is what causes elements to form ions or to form bonds with other elements. It causes them to give away or acquire or share electrons so that they have a full outer shell, just like those cool noble gases. So yeah, atoms gain or lose electrons to achieve this octet. So there's this thing I mentioned at the beginning of this video called the noble gas shortcut for writing electron configurations. Since the noble gases have all full subshells, we can kind of use them as a starting point when we are writing out our electron configurations. So let's look at an example. Actually, let's talk about it first. So let's pick magnesium for now as my example. I'm going to write the previous noble gas symbol in brackets. And so you might say, wait, which one is the previous one? Well, that's going to be my dude neon, the noble gas with the lower atomic number. And when I write in neon in brackets, that's going to count for all of the subshells filled by neon. And so we'll just put that in brackets, and then we'll start to write all the subshells filled after that for our proper electron configuration. So let's use strontium now as an example. My dude strontium 38, it would kind of be annoying to write out the full electron configuration for this. But I can go, and I can say, what was the previous noble gas? Oh, it's krypton. So I'll put krypton in brackets, and then I will finish the electron configuration normally. So I'll say, all right, krypton, everything's full there. So now I'm at strontium's block, the 5s, so I'll write in 5s2 for strontium. This is the same thing as writing that full lengthy electron configuration, and as you can see, it saves a toot load of time. Yeah, so 5s2 for my dude strontium. Let's practice with a few different dudes. So we got palladium, arsenic, calcium, tin, and chlorine that we'll go through. Cool. So first up, palladium down here. what are we going to do? Well, we're going to, well, why don't you pause the video and try and come up with this on your own? Sweet. Sweet, you paused the video. Let's go through it together. So I'm going to look at palladium. I'm going to locate the previous noble gas, and I'll do the rest of the electron configuration from there as normal. So I'll go through my 5s2 and then into my 4d block, because we go 3d, then 4d, and it's 1, 2, 3, 4, 5, 6, 7, 8 spaces over to palladium. Cool. Why don't you pause the video and try going through arsenic now? Okay, cool. Well, let's go through this together. So arsenic is located yonder. So arsenic is number 33. So I'll look at my previous noble gas. That's going to be argon. And then I'm going to continue my noble gas configuration from there. So I'll fill up my 4s2, this full 3d block, and then I'll hit the 4p. 4p goes 1, 2, 3 for arsenic. Neato, neato. Why don't you pause the video and try going through these next 3 ones by yourself? Cool. Sick. Let's go through those together now. Calcium is here. So our previous noble gas is again going to be argon. And we're just going to fill up our 4s2 after argon. Tin. I do down here, atomic number 50. My previous noble gas is krypton. And so after krypton, I'll fill up the 5s2, the 4d10, and then I'll put 2 electrons into my 5p. And then last up is my friend chlorine. Well, before chlorine comes neon. And after neon, we'll fill up that 3s2, and we'll put 1, 2, 3, 4, 5 electrons into that 3p subshell. Cool. Well, I hope you feel pretty rad about those dudes. Let's keep rolling on here. Oh my gosh, and look at those cute otters. And look at those cute baby otters. Oh my gosh. Oh, and there's a baby panda just to mix it up. Cute little fuzzy things. All right, let's talk more about that octet rule and ions and electron configurations. So we're going to specifically be talking about ions of the main group elements. Main group elements form ions in order to achieve the octet, like pretty much always, and that would be having 8 valence electrons. So they're going to either gain or lose the fewest number of electrons possible in order to reach an octet. So that means that an element with 6 valence electrons, it's going to be easier for that to gain 2 electrons rather than to give away 6 electrons. It's easier to get 2 things than to give away 6 things. And similarly, an electron with 3 valence electrons, it's going to be easier for that dude to give away those 3 electrons than it is for it to pick up another 5 electrons. Easier to lose 3 than it is to gain 5. So it's going to use either gain or lose the fewest number of electrons possible to either empty its shells or get an octet. So let's look at some examples. Let's start with my dude sodium. Well, here is my electron configuration for sodium. What do you think the electron configuration, or rather, based on this, what charge do you think sodium will form as an ion? And what do you think the electron configuration for sodium as an ion will be? Pause the video and think about that. Well, sodium is going to want to give away one of these electrons. It has 1 electron to give away before it has any full second shell. So it's going to lose 1 electron, and that's going to make it be a positively charged ion. And as it turns out, pretty much all of our main group elements will have the same electron configurations as noble gases when they form ions. Did I say that? Main group element ions? They're going to have the same electron configurations as those noble gases. And that's because those noble gases are very stable, and that's because these main group elements are going to form ions to become stable. So let's look at another example. Why don't we check out nitrogen? Why don't you first start by coming up with the electron configuration for nitrogen? And then I want you to try and predict what the charge on nitrogen will be. And also, what would the electron configuration for a nitrogen ion look like? Pause the video, try that meow. Okay, sick. Well, let's go through it together. First of all, our electron configuration for nitrogen is pretty easy peasy. We'll fill up that 1s, and then that 2s, and then it's 1, 2, 3 into that 2p block. So nitrogen is going to want to gain electrons because it already has 5 electrons in its outermost shell, 2 from that 2s and 3 in the 2p. So it's going to be easier for it to gain 3 electrons than it is for it to lose 5. So as a result, nitrogen we can expect will gain 3 electrons and have a -3 charge because it'll have 3 extra electrons. And it will end up with the same electron configuration as a noble gas, neon, the nearest noble gas to nitrogen. Nifty. Why don't we look at one more of those? Why don't we try and figure out for chlorine? What is the noble? Well, we'll start with what is just the electron configuration for chlorine. Then what charge do you think a chlorine ion will form? Or rather, do you think chlorine will gain or lose electrons? And then what charge do you think a chlorine ion will have? And what do you think the electron configuration for a chlorine ion will look like. Pause the video and think about those things. Well, here's our electron configuration for chlorine. Not too shabby. We'll fill up our 1s, and then our 2s, and then our 2p, and then our 3s, and we'll put 1, 2, 3, 4, 5 electrons into that 3p. So that's pretty easy. And then at that point, chlorine has almost a full third subshell. It just, or rather, the full S and P, full octet in its third shell. There are 7 electrons in the subshell right now. So if we put just one more in, it will be nice and happy and have a can't say words, a full third shell. Jeez. And so the electron configuration for a chlorine ion would look like something with a full third shell. It would be identical to the electron configuration for argon. All right, well, let's look at one more thing here. So let's look at this last thing. If we know the electron configuration for an element, I want you to figure out what is going to be the charge of the ion that an element with this electron configuration will form. So figure out what element has this electron configuration, and then figure out what is the charge of the ion that this element will form. Pause the video and think about that now. Sweet. Well, what we can do here is look at 3p1. That's our final address. That tells us this is aluminum, for one thing, because this is the 3p, and this is the first element in there. But we can also say, all right, in the highest energy level, this has 2 electrons in the S, 1 electron in the P. So it's going to be easier for this to give away those 3 electrons than it is for it to pick up 5 electrons. So I can say aluminum is going to lose electrons to have a full second shell. Aluminum will like to form a +3 ion that has the same electron configuration as neon. Neato, neato. Well, that's the end of this video. I hope you feel like you understand, first of all, how to write noble gas configurations for noble gas electron configurations, I should say. And I hope you understand why noble gases are stable. It's because of that octet rule. I hope you understand why that octet rule is important for other chemistry, including formation of ions. And I hope you had a good time looking at those fuzzy animals. Ta-ta, and have a great rest of your life.